Hello and welcome back. So in the previous videos we started talking about integration of complex functions, and in particular, in order to understand what complex integration means physically, we started talking about how we can think of complex functions or mappings as vector fields in the two-dimensional complex plane. So let's sort of remind ourselves of a couple of notions of vector fields, and in particular focus on the two-dimensional case, and this will help us sort of build on, and we'll quickly see how sort of this will help us build on the ideas of complex integration, as well as understand complex mappings much more vividly. So the two ideas in particular are flux and circulation of a vector field through a region of space. So let's get started with the idea of flux first. And flux essentially means flow. So although flow would suggest something like fluid flowing through a region of space, and that's actually a very good picture to keep in mind when we are thinking of what flux means. But the idea of a flux is generically applicable to vector fields, which is what we are discussing for now, even for scalars, for instance. But so let's think of what flux is by imagining some curve C, let's say in the two-dimensional plane. And let's say we have some vector field which we denote with the symbol E in this region of space. So flux is essentially the amount of this field flowing through the curve per unit time, for instance. So again, there I've sort of borrowed the ideas of fluid flow. So for instance, if you're given the velocity of a fluid, then essentially the velocity of the fluid times the length of the curve through which it's flowing. The normal component of the velocity of the fluid times the length of the curve through which it's flowing will give us flux. So if you think of the dimensions of that quantity, then velocity of the fluid times, so velocity of a fluid will have dimensions of length over time, whereas the length of the curve would have dimensions of length. So length would have dimensions of length. And so if we take the product of these two, velocity times length, we'll have something with dimensions length square over times, and this is what would be the dimension of flux for the case of, let's say, fluid flow. And in two dimensions, it makes this sort of length square is essentially area divided by time, and area is essentially how we will capture the idea of amount of fluid in two dimensions. In three dimensions, we typically talk of volume, let's say this much liters of fluid, but in two dimensions we'll have to talk about area of a fluid. So the amount of fluid through this curve per unit time would be one way to thinking about flux. However, this idea is much more general. Like, we can also think of E as an electric field, for instance, and in general any other sort of vector field we can apply and think about the flux of that vector field. So to define this more formally, let's sort of imagine a small segment of the curve of length ds. Let's say we are at some point P here, and we imagine a small segment of the curve ds, and let's say the vector field is pointing like this here. So fluid that will pass through the curve, in order to capture the idea of fluid flowing fluid passing through this curve, what we'll have to do is we'll have to take the normal component of the vector field to this segment of the curve, and because that will be the component that will actually cross or flow through the curve. So again, as in a two-dimensional plane, we can sort of decompose any vector in two independent basis along two independent basis vectors, and one choice for this particular point P could be along the tangential to the curve, and the unit vector along the tangent to the curve we can denote with the symbol t hat. Likewise, we'll have a normal to the curve, which we can denote with n hat. And so this vector field, for instance, we can write as in terms of its normal component, normal to the curve, plus tangential to the curve, the component which is tangential to the curve. So that will be one decomposition of the vector field along two along two mutually orthogonal directions. So this will be the normal component, and this is the tangential component. So the infinitesimal flux flowing through this part, this segment, ds segment of the curve, can be defined as df is the normal component of the field E dot n times the length of the curve. Again, if you apply this to fluid flow, then E, essentially the field that we'll be referring to could be the velocity field. Then the velocity field times the length will give us an area divided by time, and that will be the amount of fluid crossing this segment per unit time. So that's infinitesimal flux, and if we integrate this along the curve C, we get the total flux through the curve C, which is essentially this. Okay. So one way to this is just a one-dimensional integral. One way to think of this is, again, like if I just repeat this curve here, then what we're doing is we're breaking this down into small segments like this. Okay. Then we are calculating the normal component of the component of the field at every point. This, for instance, the normal could be this here. The magnitude will differ. Okay. And then this normal component we are multiplying with the length of the segment. So essentially we construct a rectangle like this. So we construct these rectangles and so on and so forth. And it's the sum of areas of these rectangles, which is, so this is the area of one such rectangle, and the sum of areas of these rectangles essentially gives us the flux, total flux through the curve C. Okay, so that's one important idea coming from vector fields. Now, so far we have only considered the normal component of the curve, normal component of the field. But what if we consider the tangential component? Then we have the idea of what is called the work done, or circulation in some cases. So again, this notion comes from imagining the vector field as, let's say, a force field. And if you recall from let's say basic ideas in physics, then we have some curve in space. Then the work done by a force field is essentially the component of the force field along the curve times the distance that you move along this curve, and then you just sum this up to get the total work done as we move along this curve. So essentially work done is therefore for a vector field given by the tangential component, which is you take the tangential component multiplied by the infinitesimal line segment, and this gives us the infinitesimal work done by the field E. So again, the terminology work and flow might suggest that they are applicable to only one kind of field, but that's not the case. These are applicable to any vector field. It's just that we sort of chosen to remain with the same terminology. So this is the infinitesimal work done by the field as we move a small distance ds along this curve, and then if we integrate this along the curve, we get the total work done, or circulation along the curve. Work done, or we can also think of this as, sometimes it's called circulation. Okay, so these two important ideas from general, which are generically applicable to any vector fields. We'll see how they sort of enter our discussion on integration of complex functions quite naturally, and lend a very vivid and physical meaning to complex integration. So let's continue with these ideas in the next part of the video, and we'll see that in fact a lot of other ideas also sort of come into picture, which is in particular here we have just considered an open curve C, but what if we consider a closed sort of region of space with a closed loop? Then we can see that the flux through the closed loop that we calculate from the value of the vector fields at the boundary of the loop are related to what's happening in the interior of the region of space, and likewise the circulation that we compute by moving along the boundary of the curve is related to what's happening in the interior of the curve, interior of this region of space, and these essentially lead to what are called Gauss's theorem and Stokes' theorem, and again all these will sort of help us understand complex integration in a much better way. So we'll sort of talk about these ideas again, and see and carry on with our discussion of complex integration soon. So hope to see you soon. Thanks for watching.